Okay, so we want to find the moment of inertia, the area moment of inertia of this cross-sectional area about the x-axis. So again, we're going to break it up into three pieces. Number one will be that triangle, number two will be the rectangle, and then number three will actually be the hole. And I want to find the moment of inertia of each one of these about the x-axis. So I find the centroidal moment of inertia of each shape plus the area of the shape times the distance between the axis, the centroidal axis that we look up in the back of the book, and the x-axis given here. So that's the parallel axis term. So we'll go ahead and start with number one. Okay. For a triangle, I look up in the back of the book, and the moment of inertia of a triangle about its centroidal axis is 1/32 base times height. 36, excuse me. Base, which is 300, and my height is 200 cubed. And again, what I'm doing here is I'm taking it about its centroidal axis right here, okay? Which that distance between the x-axis and that centroidal axis is going to be 1/3 of the height 200. Okay, so the height's 200, the base is 300, so I get 136 times 300 times 200 cubed. Now the area of a triangle is 1/2 base times height, so 1/2 300 by 200. Okay, and then that again, the distance between that centroidal axis and the x-axis is 200 over 3. Okay, and I'm going to take that squared. So from that, I find the moment of inertia about the x-axis of that triangle is 200 times 10 to the 6th. Okay, so 200 million, and that'll be millimeters to the 4th. Okay, now I'll do the same thing for the rectangle, number 2. Look up a rectangle, moment of inertia about its centroidal axis is 1/12 base times height, where the base is 300 and the height is 200. Okay, so similar, it's just 1/12 rather than 1/36 like it was for the triangle. Okay, the area of a rectangle is very simply 300 by 200. And then again, I'm looking for the distance between the x-axis and the center of that rectangle, which is just going to be 100 millimeters. And I square that. So that's the parallel axis theorem for the rectangle, and the rectangle gets to be 800 times 10 to the 6th. Okay, so the moment of inertia of that rectangle about the x-axis is 4 times bigger than the triangle. That's because the area is bigger, as well as it's a little bit the centroid is a little bit further away from the x-axis. So both of those things cause a larger moment of inertia for this guy. Now I've got a hole, right? So I look up the moment of inertia for a circle, and it's 1/4 pi r squared. So I go 1/4 pi, and then r of this is going to be 75, excuse me, to the 4th, not squared. That's the moment of inertia about the center of the circle. I need to do parallel axis term. So then I take the area of that circle. That is pi r squared, so 75. Okay, and then I take that times the distance between the x-axis and the center of the circle, which of course is 100 squared. Okay, and what that gives me from that parallel axis theorem is 202 times 10 to the 6th millimeters to the 4th. And I want to put a negative in front of that, and the negative is because it's a hole, right? It's actually being removed from this, so that when I find my total moment of inertia about the x-axis, I'm going to go 200 plus 800 minus 200. Again, all of these are times 10 to the 6th, and I get 798 times 10 to the 6th millimeters to the 4th. So again, break this up into pieces. Using parallel axis theorem, find the moment of inertia of each one about the axis of interest, recognizing that when I add these together, I'm actually going to subtract off that should be a 202, little typo there. subtract off the circle because it's a hole, it's being removed. So to find that total when adding them all together.